And hi, everyone. I'm Shuang. So I'm a postdoc researcher in Water Research Center and Water UNSW, and I completed my PhD also in UNSW this year. And 2 weeks ago, I just attended my graduation ceremony. So I'm very thrilled to have the opportunity to give my presentation about my PhD projects. And probably I will also cover a little bit of my current work. So as Travis' introduction, my PhD work is mainly supported by the Nuisance and Harmful Algae Science Practice Partnership with Melbourne Water. So harmful algal bloom is a worldwide issue. It damages water health and it poses threat to environment, public health, and economy. So let's see some headlines of harmful algal bloom in 2022. You can see this year, harmful algal bloom still occurred in different countries, and it causes around $14 billion to fix algal bloom issues. So that is a huge economic loss for dealing the harmful algal blooms. And currently, harmful algal blooms, the study of harmful algal blooms focus on the large lakes and coastal waters. However, limited studies focus on small lakes. So that's why my PhD research is mainly about harmful algal blooms and water health in small water bodies. Small water bodies, constructed water bodies, including the wetlands, ponds, and lakes, are designed to attenuate floods and enhance water quality. Although those small constructed water bodies are designed based on the design guidelines, many water bodies still experience harmful algal blooms. So, and with more and more small constructed water bodies being built worldwide, there is an increasing harmful algal bloom risk under the anthropogenic and climate change. So it is important to improve our knowledge of harmful algal blooms in small constructed water bodies. And in my research, I mainly want to answer 3 questions. The first is, can water body design guidelines be improved to limit harmful algal blooms? And the second, how well does remote sensing supplement field data in small water bodies? And the third, what affects urban water body health? And then in my current work, continued with my third project, I'm currently working on the using remote sensing on global water bodies watercolor. So first, let's look at my first project. So my first project is a combination of review and data analysis. So actually, we reviewed in total 66 international design guidelines on harmful algal bloom limit, and then we tested the effectiveness of the design criteria identified from the design guidelines, compared them with a real-world case study in Melbourne regions. And what we found from the review first is that we found most of the design guidelines, they followed the design criteria from non-stormwater assets, and they apply empirical or rule of thumb criteria and based on the old literature. And as I said that we also tested the effectiveness of the identified key design factors. We used the Melbourne Water dataset as a case study. So here, the dataset we received from Melbourne Water was around 1,070 water bodies. However, some of them are like connected with each other, and some of them are connected with each other from the underground pipe. So after all those information, we reduced the total number into 222 water bodies. And in this map, you can also see that not all of the water bodies experience harmful algal bloom. Part of them, around 40 water bodies, have experienced harmful algal bloom. So in here, the algal bloom I'm talking about, the threshold is over 4 cubic meter. 4 milligrams per cubic meter. And then actually, we first look at the single factor analysis. So in here, you can see I choose 6 key identified design criteria from the design guidelines. So aspect ratio means the ratio between the lake water body length to its width, and microphyte ratio means that the microphyte vegetation region within the water body and compared to the water body area, and lake to what urban ratio, lake to impervious ratio, and fetch. Fetch here means the fetch distance, the maximum fetch distance among 8 directions, and SDI. SDI, the shoreline development index. Actually, it means the complexity of the shoreline. So actually, the first 4 design factors are commonly mentioned in the design factors, in the design guidelines. However, the fetch and SDI are not commonly mentioned. So let's see, for example, in the aspect ratio, the red dots are blooming and blue dots are non-blooming assets. And in here, we use the cumulative distribution function, and we want to see if the blooming and non-blooming, the cumulative percentile for each of the design factors can be significantly separate. And also the orange lines, dotted lines, means that based on the Melbourne water design guidelines, what is the current design factor, the criteria, and the orange shadow are the based on the international design criteria. What is the range of this factor? So here we can see that based on the KS test, the microphyte ratio, fetch, and SDI are the most important factor. However, the most commonly used factors such as aspect ratio, lake urban, or lake impervious ratio are not that significant. And then we also explored how the combination of multiple factors impact on the harmful algal bloom, the blooming or non-blooming. So in here, actually we use the K nearest neighbor classification, quite simple basic classification method. So for example, in the macrophyte area plus SDI, means that in here we tested the 2 combination of these 2 design factors and see how it affected the blooming in blue dots and non-blooming, sorry, the blooming is in red dots and non-blooming in blue dots. So we can see that the pink area here means that under 40% of macrophyte area and under 1.5 SDI, there is a high risk of harmful algal bloom. However, this KNN is not that perfect because you can see that still some of the blooming outside the pink area exist. And I also include the right figure I put is an example that KNN does not have the ability to identify the threshold of the harmful algal bloom high risk. We also did the 3-factor combination. However, because of the time limit, I won't show here. And this is the summary of our first project. We reviewed 66 shallow water body design guidelines to see how it relates to harmful algal blooms limit and identify the key design criteria. And we used 222 constructed shallow water bodies within the greater Melbourne regions to assess the effectiveness of current design guidelines. And we suggested some improvements to water body design guidelines. And we found that simple factors does not stop water bodies from forming harmful algal blooms. However, there are key factors such as the macrophyte ratio, the fetch distance, and the SDI matters. And actually, our work has been published last year. And if you are interested and want to explore more information that are not covered in this presentation, please come to have a look. And the link of this paper has also shown here. And then let's move to my second project. My second project actually is about the utility of remote sensing on harmful algal bloom in small to medium-sized water bodies. So based on our study of the first project, we found that the biggest issue for me is that I don't have enough data, or the data is quite sparse. For example, you can see the data is sparse in space, and also even with the sites with harmful algal bloom, the temporal pattern is also sparse. There are many gaps in between different years. So we wonder, can we use another tools to supplement the field data? So we read the literature, and we know that there are a lot of studies working on using remote sensing techniques to supplement field data. So we want to see if it is applicable or efficient to use the remote sensing on the small water bodies to identify harmful algal bloom. And here we show is that in our preliminary test, we have, in here we show that for different satellites, because we know that there are different optical satellites, for example, MODIS, Landsat, Sentinel, or other very hyper spectral satellites. And we want to see how the images looks like for different spatial resolution, temporal resolution, spectral resolution. And here we choose 3 different size water bodies. And this is how it looks like. And our hypothesis, initial hypothesis, is that with higher resolution, like periscope, we should have more accurate detection skills. So we use, but however, there are other like interference factors. For example, the vegetation surrounding or submerged macrophyte within the water bodies, and also the pixels between the lakes and land. And considering the lake size, we have to use another lake, like Grahamstone Dam, because first is that this dam is large enough to cover the normal small to medium-sized water bodies. For example, in here, I constructed from 6 representative synthetic water bodies ranging from 0.001 to 5 square kilometers within the water bodies. And also this Grahamstone Dam is in the southeast New South Wales. and it is mesotrophic cyanobacteria lakes. And also another reason is that this green hamstone dam has very long data record. It can trace back to 1980s. And however, in here, I only showed from 2016 is because if I compare these three satellites with different resolution, the planiscope, the earliest of the planiscope is around in 2016. So to match with the planiscope time range, so I only choose Sentinel-2 and Landsat 8 also within this after 2016 to 2020. Here is, so actually I also show here is during this period from the September 2018 to October, there was a big bloom, and I choose one day, the nearest date of one bloom in 2018 September, and show the RGB image. So actually we in our study we used two methods. One is using bio-optical empirical algorithms, and the second is using a machine learning technique self-organizing map. So based on the 21 empirical algorithms we summarized from the existing literature, we tested them first. And actually, we also did some pre-processing of the satellites, and also the satellite data we downloaded from the Geoscience Australia from the NCI platform. So first, let's look at one algorithm of this Sentinel-2. So different color means a different synthetic water body, from like green, so the smallest, to the dark blue, the largest. And we use the Spearman correlation showing here because of the biased distribution of the satellite derived data set. And actually, if you only look at one algorithm using the Sentinel-2, there's no so much differences between different lake size. And it also happened in the other algorithms. In here, I only showed 4 algorithms. Although the correlation value is a little bit different. And this is the same thing we found in using Landsat 8. So not so much differences between different lake area. Although the Landsat 8 has higher correlation than Sentinel-2. And if we also compare Sentinel-2 Landsat 8 with the planiscope, we can see that actually planiscope has a least correlation. So which is opposite to our hypothesis. So we were wondering probably it is because calibrated satellites of Sentinel-2 and Landsat 8, and also the algorithms was originally developed based on the Landsat 8, Landsat, and planiscope has is less calibrated satellite. Some reasons probably. And then we also use this machine learning technique, self-organizing mapping, because self-organizing mapping can project the data into 2-dimensional map, and it can separate the pixels values of the similar pattern from the not similar pattern. So it is a kind of like unsupervised clustering techniques. That's for us to identify, to cluster the dates that identify as blooming or non-blooming. So in here, we can see that we show this cell densities distribution of Sentinel-2, Landsat 8, and Planiscope. We can see that for smaller water body size, actually Sentinel-2 and Landsat 8 has some ability using self-organizing map, ability to differentiate the blooming and non-blooming. Oh, and also this the dashed lines of each of the box plot means that the significant differences using Wilcoxon test is smaller than 0.05. But Planiscope, we still can't find the significant differences. And except for these water body size versus which satellite can be used, and we also find other challenges using satellite to improve the accuracy of harmful algal bloom detection skills. First is the challenge. First challenge is the algae dynamics. So algae don't stay in the water column still, so it can spread vertically across the water body surface, and also it can float up and down within the water column. And it depends when the satellite pass, and also the time when you collect the samples. And the second is that the algae mixing with macrophyte at edge. So actually, there are some algorithms, there are some studies to differentiating the algal bloom based macrophyte within at the edge. But in our study, I didn't use those algorithms. In fact, I used those synthetic circles to remove this interference. And the third challenge is the correction models. Actually, when I pre-processing the data, actually we use some terrain correction, atmosphere correction, different correction models that will also bring the uncertainties into our data set. And the first is the satellite overpass or visit time. So that means that different, as mentioned in challenge 1. So when you collect the samples, the ideal scenario is when you collect samples and you have the nearby satellite images, but most of the time they are not matched, so you have less data set for you to further processing or analysis. And the fifth challenge is cloud and haze. So it also means that although you can use cloud or cloud shadow masking algorithms, but you still have less data set than your sampling you expected. So this is a summary of my second project. We need more studies of harmful algal bloom detection on small water bodies, and we identified challenges on harmful algal bloom detection on small water bodies, and we tested the empirical algorithms and the machine learning techniques on Great Hamstone Dam to check their accuracy. Actually, we also check the accuracy, the POD, FAR, although I didn't show in my presentation. We found no differences, no significant differences on harmful algal bloom detection for various lake size, and Landsat 8 and Sentinel-2 has better detection skill. And also, if you are interested in more details, this research has also published in Science of the Total Environment, and you can have a look, and the link is shown in below. And then move to my third project. As I showed that satellite processing and choose which satellite is an issue. But actually another big issue that confuses me a lot is the watercolor variation. This is an important issue because watercolor variation can cover the harmful the algae detection, the algal bloom detection signals in the water bodies. So we step back a little bit to investigate the watercolor, the baseline watercolor and the watercolor change. What affects those watercolor change and what is the baseline watercolor of those water bodies? So here we can see that in space, there are variation of the watercolor in different water bodies. And also in time to time, from day to day or from year to year, there's different watercolor, so temporal variation as well. And watercolor is an indicator of water health, water quality, or the environmental stress from the surrounding catchment. And watercolor can be like blue when it is clear, but with the pollutants flowing into the water bodies, it can also be green or brown or red, different watercolors. And then we talk about the what drivers influence watercolor change. For example, in a catchment, there are different land use and water runoff from the rainfall flowing into the water bodies. And actually, yes. So in the water body itself, the watercolor can be influenced by algae, suspended solids or TSS, and color dissolved organic matter. And from the environment, it can be affected by geophysical, anthropogenic, and climate variability. And within the catchment and also the water bodies, it can be affected by different geophysical factors. For example, the lake geometry, linking with the catchment characteristics. For example, the land use, the soil type, the geographical characteristics. And for long term, it can be also affected by different climate drivers. For example, the ENSO, that's El Nino Southern Oscillation, IOD, Indian Ocean Dipole, and SAM. That's the Southern Annular Mode in a longer time. So actually in this study, we did two things to understanding the distribution, spatial distribution of the baseline watercolor and understanding what drives the temporal variation of watercolor. So baseline watercolor here, I mean, is the average, the watercolor across the water bodies. And in our study, we used two different methods to calculate the watercolor. One is using dominant wavelengths. So it is a kind of like how your eyes perceive the true watercolor. And it is based on quite 8 lines equations. Only use the blue, red, and green bands from the surface reflectance of the satellite. And then we also use the empirical algorithm, for example, the ratio between green band to red band. And in this study, we used the Landsat 8, and also we used the Sentinel-2 to compare how these two correlate with each other. But in here, you can see that in Melbourne, the greater Melbourne regions, within these 145 water bodies, the dominant wavelengths actually range from yellow to green, from green to yellow. That's from the 525 to 580. Probably you can't see it clear the differences. So that's why for easier visualize, we also show this the ratio of the green of red. And then we want to see how can we explain the spatial variability. So for easier interpretation, from now I only discuss about the dominant wavelengths. So actually, what we use is that we use the multivariate linear regression with stepwise, with backward stepwise selection method, and then we generated this observed average dominant wavelengths versus the modeled average wavelengths. And you can see that using the multivariate linear regression, it has some skills to show that. Oh yes, and also the input factors we use is the static factors, including the lake characteristics, the catchment characteristics, and the average climate data. So all of these data are the same as what I used in my first project. And we can see that there are two types of key factors after the stepwise selection. One is design controllable factors, means that when you design the water bodies, those factors actually you can control in your design phase, and non-controllable factors means that you can't control them. So first is that the area of the water bodies to the catchment area, and the second is the macrophyte ratio within the water bodies to the water bodies area, and the third is SDI, the complexity of the shoreline. And the non-controllable factors, for example, the geology, the soil type, the stream odor, means that the location where the water bodies locate, and the wind, the averaged wind. And then we want to see, can we explain the temporal variability? So in here, for each of the water bodies, for individual water body, we developed also the multivariate linear regression. And based on the R-square, we separate them into two different water types. One is the water bodies can be explained by the climate factors, and the second is cannot be explained by the climate factors. So the climate factors in here we use is time series from 1980s to 2021 of the rainfall of the past 30 days, temperature of the past 30 days, and SPI, and for the, and we also use global drivers, for example, the SOI, IOD, and SAM. So we can see that 1/3 of the water bodies actually affected by climate drivers. And actually, we also ranking the importance of those climate drivers, and we found that actually the regional climate factors, for example, the rainfall temperature, is more important than the global drivers. And I think it's also because of the limited geographical location, distribution within this Melbourne, the Greater Melbourne regions. And then the summary of my third project. So actually, this study addresses the gap in watercolor in small water bodies. So we want to explore the watercolor variation, the temporal variation, the spatial distribution of the watercolor in small water bodies. And actually our ultimate goal is to link it back to see how it can improve the harmful algal blooms detection. And then instead we identify 2 water body types, can be explained by climate drivers and cannot be explained by climate drivers. And for the first one, we know that how the climate drivers affect those water bodies. However, for the second type, we need more understanding of the watercolor change process. And we need to collect the field data on the potential factors. Remember, in the spatial analysis, we use the static factors like and the design controllable factors. However, some of the design controllable factors, for example, the water depths, actually, we don't have those data, the data limitation, because Melbourne Water didn't provide this data, so we are lack of the data. And then, And then we need to expand the local findings to global scale. Actually, this is my current postdoc work. I can spend a little bit more time on this. So this is using the remote sensing on watercolor of global water bodies. It used Landsat 5, 7, and 8, covers 35 years. That means from 1986 to 2021 data set. And we also, like what we did in our second and third project, we also did the pre-processing, for example, using the cloud or cloud masking algorithms to get the clear images. And also we use water extend algorithms to get the water pixels. And we use we only choose the water bodies within the average, without the arid and poor regions, using Köppen climate regions. And also we check the temperature of the water bodies. So we ensure that actually we look at is the water pixels. And then we also did the spatial distribution, and we found that yes, there's a clear differences, spatial differences. And we also try to explain the temporal variation. And this is an ongoing postdoc work, so I haven't finished yet. And another point, the next one, yeah, the next point is that we need to test if the dominant wavelength method measured is what we need. Because in my third project and my fourth project, I used the dominant wavelength method to generate the watercolor from satellite. However, I think I need more tests to check if dominant wavelength method measure is the water quality. So first is that we need to generate integrated water quality index that can be represented by the dominant wavelength method. And the second is that we also want to explore other methods. For example, PCA using the multi-band reflectance data, and to identify the either algal bloom or this watercolor variation. So actually, this is an open discussion point. So I'm also happy to discuss with other their people. I know you are very professional in different mathematical machine learning techniques, so I'm happy to discuss. But actually the PC idea, previously I discussed with Richard from there. And yes, and then this is my research team. My main supervisor, Fiona Johnson, joint supervisor, William Glamour, and secondary supervisor, Boyan Temperic. And my supervisors are really supportive and helpful, and give me a lot of valuable suggestions and guidance during my PhD studies. I'm very grateful to be supervised, to work with my supervisors. And Nick Crosby from Melbourne Water, he's also a very kind, friendly, and very helpful person. He provided the many data and information for me to proceed my PhD from the beginning. And myself. Oh, and that's it. So thank you for your listening, and I'm very happy that I can give this presentation. And if there's any questions, please let me know in the chat box or discussion. And this is my contact details. And thank you.